A turbocharger forces more air into the cylinders of a turbo engine, increasing engine power. By using the energy from exhaust gases to turn a turbine, it compresses incoming air and increases the engine's fuel efficiency. This enhances performance and fuel efficiency by enabling a smaller engine to produce greater power. Number 8. Turbocharger main components. A turbocharger's core components are the turbine and compressor, which are both mounted on a solid shaft. The turbine section consists of a turbine wheel housed within a specially shaped turbine housing that directs exhaust gases from the engine to the blades of the turbine wheel. This housing is precisely engineered with a volute spiral shape that increases the velocity of exhaust gases and guides them efficiently onto the turbine blades. On the opposite end, the compressor wheel or impeller is enclosed in the compressor housing, which draws in ambient air and accelerates it before compressing it. The compressor housing's volute and diffuser sections convert the high-velocity air from the compressor wheel into pressurized air that feeds into the engine. The turbine and compressor are directly linked by a high-strength shaft, which allows energy transfer. The turbine extracts power from exhaust gases and transfers it mechanically to drive the compressor. This integrated design enables effective energy recovery from exhaust gases, boosting intake air pressure and ultimately engine output. Number 7. Turbine powered by exhaust gases. Exhaust gases leaving the engine cylinders during the exhaust stroke are hot, high pressure, and energetic. These gases enter the turbine housing where, due to the housing's narrowing geometry and nozzle design, their pressure energy is converted into kinetic energy in the form of a high-speed gas stream. This stream impacts the turbine wheel blades, driving the wheel's rotation. The design and shape of turbine blades are critical to ensure maximum energy extraction, as they must efficiently convert the flow's kinetic energy into rotational energy for the shaft. The turbine wheel can reach rotational speeds in excess of 150,000 to 250,000 RPM, tapping the waste energy of the exhaust gas that would otherwise simply exit the engine and be lost to the atmosphere. After passing the turbine blade stage, the exhaust gases expand further in pressure and temperature before leaving the system. This sequence transforms exhaust gas energy into usable mechanical torque to operate the compressor. Number 6. Compressor compression of intake air. The compressor wheel rotates at extremely high speeds, powered by the turbine shaft. As the compressor spins, it draws ambient air through the intake via an opening called the inducer. The air is first accelerated axially, then flung outward radially by the centrifugal force of the rotating blades. This centrifugal compressor design rapidly increases the velocity of the air. Next, the air enters the compressor diffuser, a vaneless, diverging passage that converts the kinetic energy high velocity of the air into pressure energy by slowing the airflow. The compressed air then collects in the volute, which further helps maintain steady pressure as the air flows out of the compressor housing and into the engine intake. The design features such as inducer diameter, diffuser shape, and volute size are optimized to achieve a high-pressure ratio and maximum flow with minimal losses, allowing the turbocharger to deliver dense, pressurized air to the engine for combust. Number 5. Increasing air density to boost power. The reason a turbocharger enhances engine power is that compressed intake air contains more oxygen molecules per given volume than atmospheric air. This higher oxygen content means the engine can inject more fuel while maintaining the optimal air-fuel ratio for combustion stability. The dense compressed air entering the cylinders results in more intense combustion, higher peak cylinder pressures, and increased torque output. Therefore, a smaller engine fitted with a turbocharger can match or exceed the power output of a larger naturally aspirated engine, achieving greater power density. This principle allows for engine downsizing, where vehicle manufacturers design smaller displacement engines with turbocharging to maintain performance while reducing weight and improving fuel economy. However, the increased combustion intensity requires robust engine components and precise control of parameters like air temperature and boost pressure for reliable operation. Number 4. Efficiency recycling exhaust energy. One of the fundamental efficiency advantages of turbocharging lies in its use of exhaust gas energy, which is normally wasted in non-turbocharged engines. Unlike superchargers, which draw mechanical power directly from the engine's crankshaft and cause a parasitic power loss, sometimes up to 20% or more, turbochargers are driven solely by the energy in the exhaust gas flow. By channeling the exhaust through the turbine, turbochargers convert exhaust gas pressure and heat back into useful mechanical energy, powering the compressor to increase intake air pressure without additional fuel consumption or mechanical load on the engine. This recovery of waste energy improves overall engine thermal efficiency, contributes to better fuel economy, and reduces emissions by allowing more complete combustion. Number 3. Intercooler's role in cooling compressed air. Compressing air inherently causes an increase in air temperature due to the thermodynamic principles of gas compression. Hot compressed air is less dense, which reduces the amount of oxygen that can be supplied to the engine and increases the likelihood of engine knock premature combustion, which can damage engine components. To counter these effects, turbocharged engines typically incorporate an intercooler, a specialized heat exchanger that cools the compressed air before it enters the engine intake manifold. The intercooler works by transferring heat from the compressed air to the ambient atmosphere through its radiator-like construction, usually employing aluminum fins for efficient heat dissipation. Cooling the intake air increases its density, allowing even more oxygen into the cylinders, enhancing engine performance and protecting the engine from heat-related damage. Number 2. Turbocharger speed and durability. Turbochargers operate under extreme mechanical and thermal conditions, with shafts rotating up to 250,000 revolutions per minute and components exposed to exhaust temperatures exceeding 700 degrees Celsius, 1300 degrees Fahrenheit. To withstand these demands, the turbocharger's central hub rotating assembly, which houses the shaft, uses advanced bearings such as floating journal bearings or ball bearings that minimize friction and wear at high speed. Some CHRAs are water-cooled to reduce the temperature of lubricating oil, preventing oil breakdown and increasing durability. Seals on both the turbine and compressor sides prevent leakage of oil, exhaust gases, and intake air. The precision engineering and specialized materials enable the turbocharger to maintain reliable, high-speed operation while enduring stresses from thermal cycling and mechanical loading. Number 1. Impact on engine size and efficiency. The introduction of turbocharging has revolutionized modern engine design by allowing engine downsizing without sacrificing power output. Turbocharged engines can deliver power comparable to much larger naturally aspirated engines because they supply more oxygen for combustion, allowing more fuel to be burnt efficiently. This downsizing reduces engine weight and size, yielding benefits such as improved vehicle handling, better weight distribution, and more flexible packaging under the hood. Additionally, smaller displacement engines generally consume less fuel and emit fewer pollutants, helping manufacturers meet stringent environmental regulations. Turbocharging also promotes better thermal efficiency and reduced engine pumping losses, contributing to an overall advancement in fuel economy and emissions reduction in contemporary vehicles. If you want, I can provide a brief, stepwise illustration of these points as well. If you liked our video, please hit the like button and subscribe to our YouTube channel.